In this video, we'll be talking about the inverse Laplace transforms. The formula and properties we use here are pretty much the same as the regular Laplace transforms, just in reverse. So let's start with a simple example. Now we already know that the direct Laplace transform of a power of t is going to be this. So to find the inverse, we will compare this with our expression. From the formula, we can see that s power 5 matches s power n plus 1. So this means n plus 1 equals to 5 and n is equal to 4. Now we know that n is equal to 4, and here it is n factorial, which is missing here. So to match the full form of the formula, we will be multiplying with the 4 factorial in both numerator and denominator. Now we take the Laplace inverse of this entire expression from here to here, which is going to be giving us e power 4. We are going to write our final answer as e power 4 divided by 4 factorial. Now let's take a look at another example and find its inverse Laplace transform. Looking at the expression, we notice something important. There is no s in the numerator, which gives us a hint that this matches the form of the sine formula. Remember, the Laplace transform of sine is this, and now we are going to try to match our expression to this form. We can see that we are having 64 in the denominator, whilst it is a squared here. The a is a constant, so we will be equating a squared equals to 64, and taking the under root, we get the value of a equals to 8. But we are missing 8 in the numerator. So like we did in the previous example, we will multiply 8 in both numerator and denominator. Now this matches our exact form of the sine 80. And we will be taking this part over here, making it sine 80. So our final answer is going to be this. Now, let's find the inverse Laplace transform of this more complex fraction. We will be using the partial fractions to break it into simpler pieces. Here, I have already carried out the partial fractions and found the values of a, b, and c. We found the value of a by setting s is equal to 1 and substituting it here. Value of b, I found it by placing s is equal to -2 and substituting it here. And similarly for c, s is equal to -4, I substituted it here. We have found the values of a, b, and c, respectively, and substituted it in the original equation after the decomposition. Then we will be applying the Laplace inverse here entirely. And using the linearity property, we will be pulling out the constants 1 by 15, -1 by 6, and 1 by 10. After applying the linearity property, we can easily take the Laplace inverse. We know that this one is going to give us Laplace inverse e power positive t. This is going to give us e power -2t. And this is going to give us e power -4t. Now let's take a look at this example. At first glance, we can see that the expression doesn't directly match any of the standard Laplace forms we've learned so far. It is not in the form of a divided by s squared plus a squared, which would mean sine 80, and neither it is in the form of s divided by s squared plus a squared, which would mean cos 80. So our next step is to manipulate the expression and break it into simpler parts. So we will be separating it into two terms like this. 3. Now, using the linearity property of the Laplace transform, we can handle each part separately, and we can pull out the constants. So it becomes 3 and this becomes 5 here. Now we can clearly see that this matches the s divided by s squared plus a squared, where the value of a is going to be under root 7. And this also matches the form of a divided by s squared plus a squared, where a is equal to under root 7. This is our final answer. Before we move any further, let's take an example and let's find its Laplace transformation. We will be finding its Laplace transform using the shifting property, which is shown here. The shifting property is when f of t is being multiplied with e power at. Then we will find its Laplace transform and replace every value of s with s minus a. This s minus a is this one. Now let's complete this question. Now you can clearly see that when we compare these two, the e power at is equal to e power 2t, and f of t is equal to t cubed. So we are going to rewrite our Laplace transform like this. Now here you can see that we have replaced s with s minus 2, meaning that after we're going to take the Laplace transformation of t cubed, we will be replacing every value of s with s minus 2. So let's do that. Finally carrying out this step. This is our final answer.